We will wait maybe 2 more minutes and then we'll start at 6:05. Okay, so you can see there are 5 questions. And question is very large. But the first question is to find the value of mass fraction. Okay. So we'll try to do that. All right. So how many of you have seen the this question earlier from somewhere?
Yes, sir. You have shown us a similar example to this, sir, but the values were a bit same.
Values were different, right?
Yes, sir. You have.
Okay, I don't remember actually if the values are different, but it feels like the questions are exactly same. That was an assignment from previous run, so they kept it exactly the same with probably different numbers. All right, but still rest of the people can benefit from it, so we'll try to solve it. And yeah, Sanjay, you have joined for the first time, I guess. He doesn't want to speak or what? Yeah. All right. So what are we given? We are given an equation, or rather an expression for total weight. It says there is avionics, subsystems, propulsion, other things, structural weight, payload, and energy or fuel weight. Some of the fractions are given mass fractions with respect to the total takeoff weight. Structure has 26% of the weight, and mass fraction for other subsystems is almost 5%. Power to weight ratio is given. Brake specific fuel consumption is given. Propulsion mass fraction is 5%. Maximum L by D is given. Propeller efficiency is 65%, and range is given. And non-varying aircraft weights are also given. They are 50 kg. All right. And we are asked to compute the fuel mass fraction. So what should be the strategy? How do we proceed further?
Using Braggett's range formula, sir, we can find the fuel flux.
All right, because range is given. But what should be the ideal approach? Like, I mean, not just in terms of solving this particular question, but rather
Yes, sir.
solving.
We have the formula for W naught, which is equal to W crew plus W payload divided upon empty weight ratio minus empty weight ratio minus fuel fraction ratio, and there's another term, 1 plus 1.
Okay, so then I'll ask this question. The mass fraction that we're going to compute using just the Bragg-Witt's equation for range, how accurate that will be? Can you comment on it? Like, will it be accurate, and why not?
Sir, it would be, I mean, less accurate
Why so?
rather than the, because sir, in our weight equation,
Uh-huh.
we already knew the weight that we are going to have, the fuel fraction, exact values of fuel fraction.
No, my idea to ask this question is, uh, let's let's think we want to design something and design an aircraft. Actually, if you think about design philosophy, these mass fractions that are known to us, usually they are always known to us. For example, when we want to design an aircraft, uh, we we have an aircraft in mind that is almost similar to the aircraft we want. So we can look at the historical data and find out what should be the structural mass fraction. So the numbers given in this question are usually known to us. Also about the engine, because engines are not designed for specific aircrafts. Usually, what happens is there is an engine that was designed for some aircraft, but that engine can serve in a wide variety of aircrafts. So engine is always known to us. So engine's weight, its mass fraction is always known to us. So my point is, think of it as a general design problem, and you have a certain mission. You want to accomplish a certain mission with that aircraft. Then how do you estimate the fuel mass fraction? Om, can you comment on this question? How do we in general proceed? Because in last to last session that we had, we were designing an aircraft, and we had these requirements similar to what we have right now. So we had range and other things also. So there is a philosophy. How do you estimate the total takeoff weight and uh, fuel weight, right? So I just want to invoke those things here. So rather than solving a particular question, we want to build a philosophy of how to think about a design problem. Om, do you want to say something? I think you were present in that particular session we had.
Yes,
Yeah.
so
So
there we actually dependent on the historic value.
yeah, that is accurate. But what are we missing here? Rupinder said only that we can use the Bregwitz range equation. That is one part. But what were
Yeah, but for that also we need that weight fraction. It's
yeah,
not.
that is precise. I mean, that's known to us. Okay, what are we missing here? Like, are we missing something?
Sir, Braget's range formula is only valid for cruise only. It didn't take in consideration the takeoff, landing, taxiing, and
Exactly,
other
exactly. That is what I
variables.
was asking. It does not consider the complete mission profile. And when you design an aircraft, the first thing is you know what the aircraft is supposed to do. It has to you have to start the engine, right? You will taxi this, bring it to the this runway, then you take off, you land also, right? And if it's a general purpose aviation aircraft, you might have a loitering of maybe 10, 15, 20 minutes, right? So there are different mission segments. We are only considering uh, the cruise part, not the other parts, as Rupinder mentioned. So that is the approximation here. I'm not saying that it will be very off, but I'm just saying that there is an approximation involved, and you should be aware of that. All right. So this particular question, because you have to solve in maybe probably time bound manner, and that's why uh, in this manner we are going to solve it. So so what are we going to do? Rupinder, you want to describe what's happening here?
Yes, sir. We have given the all other parameters. We just need to put in the range formula, but we need to consider in the units that we are using. Like for example, for the unit of C, which is the specific fuel consumption for the aircraft. But the weight fraction that we are getting isn't the right one that we want. First, we need to reciprocal it and then subtract to -1 to get the final mean weight fuel
Okay.
fraction.
So we will only discuss the way problem is given. So there are two things I can see. One is W naught and one is W1. So what is W naught?
Gross weight or the total aircraft weight along with the fuel.
Okay. So the situation is like this. You start your cruise at 0 and you end your cruise at 1. So wait at takeoff and wait at landing. And in between you have a range. So you consumed a certain amount of fuel here. So what's going to happen is your gross takeoff weight is sum of W1 and what?
Fuel.
Yeah, fuel. So if I divide it with the W naught on both sides, right? What are we going to end up with? 1 is equal to W1, which is fuel. No, not the fuel. W of F or W naught. So what are we interested in? Which quantity we are interested in? Is it the quantity we are interested in?
Yes.
All right. So fuel weight over the gross takeoff weight, we have 1 minus W1 over W naught. And what was the Breguet's range formula, if you can recall?
Eta by C into L by D into log of W naught upon W1.
Log of W naught over W1. So from here, you can compute the reciprocal of this number, right? So that's here. And how about C? C should have certain units. So I think it's best to compute everything in SI units, right? So C was given to us in what units? Let's go back and see.
I guess it is per hour, sir.
Yeah, it's given in HP hour. So you have to convert HP to watts and hour to seconds, right? Kilogram
Yes,
remains.
sir.
Yeah. So the number is 2265 and why there is a 9.81. Why this factor?
So it is G factor, maybe counting in the weight, convert to convert what, sir?
Because in the definition of the C, it was Newton. So kilogram must be converted to Newton. Okay. You can go
Sir, for
back and
746 we can get in watts and it is a horse HP per hour it is, sir. Just we need to convert 746 and for 3600 we need to multiply by 746 divided by 3600.
no, my question is what's the definition?
For what, sir?
Brake specific fuel consumption. What is the definition? So the definition involves probably the Newton. Okay, that's why kilogram should be
Okay,
converted
sir.
to
kg,
Newton.
yes, sir. Oh, sorry, actually I was reading something different.
Yeah. So whatever number we had, we have units like kg and then HP hour. So the equivalent will be multiplication with 9.81 HP division by 746 and 3600 seconds per hour. All right. So this is the factor in C, whatever number you had, right? Then you can use it here. And the efficiency is also given, probably 60%. You have this fraction here, you reciprocal it, and then you substitute and get the fuel fraction from here. I hope everybody now understand what we're supposed to do here. So we'll go to question number 2. The weight of the air vehicle in kilogram is. So what can we do?
So we have all the weight fraction formula, so we can put in the equation which is given above.
Mhm.
The first equation of weight.
Okay.
And the whole equation should be divided up by W naught.
Yeah. So is everyone clear about where this expression came from? If not, then I can explain. If yes, then we can move ahead. Sanjay, are you familiar with this expression WTO? Where did it come from?
So actually in the denominator,
Mhm.
when it was not only the fuel and structure variable were mentioned, not about the subsystem and propeller. So when do we add those?
I couldn't understand actually. Can you ask again?
No, when it was mentioned in the lecture, in the denominator part, only the structure weight ratio and the fuel weight ratio was there, not the
Okay.
propeller one. So when do we add that?
Okay. Because the mass fractions. Okay, so let me explain how does this work. So first we are going to look at this expression, and then I'm gonna take a screenshot of this expression from here. This is the expression we have. We copy it and bring it here. Keep source formatting. Yeah, so it's here. All right. So avionics, other, and payload. These are the known weights. So you club them together. WA, WO, and WS. You club them together, and you know the fraction of other weights. You know the fraction of this. So what you do is you write it in terms of fraction. So W sub divided by W takeoff, right? This is the fraction, and you multiplied this fraction with the WTO. Similarly, you do this for propulsion, and you divide it with takeoff weight and multiply with the takeoff weight. So what you know is this fraction, okay, not the WTO. That's why we are able to do this. Similarly, we have been able to compute the fuel fraction, and we can multiply this with WTO. Now you can take WTO as common and keep the WA.
Yeah, okay.
Now you got it right?
Yeah, yes, sir.
Yeah, perfect. But for Sanjay, we will do it because he does not know where that expression came from. So WTO is common here, and these three expression, I'll just call them W alpha, W beta, these three fractions, and W gamma. These three fractions are here. WTO is also here. So you can simply take WTO as common, and there will be 1 minus W alpha, W beta, W gamma, and on the right side, these three weights. So that's how the expression comes for WTF. AOS over 1 minus gamma. I hope Sanjay also now understand where the expression came from. Yeah, we go back and we see. Yeah. All right. So now we are asked, what is the weight of the power plant in kilogram? So we were aware of the mass fraction of the power plant, and we know the total takeoff weight. So power plant is just 5% of that. So we computed it here. Sanjay, you understand the third question, right? Yeah, he understands. All right, so we move ahead. The peak power required in HP will be, because total weight is known to us, the total takeoff weight for the takeoff weight. So P over W was given to us already. You just have to multiply this number with W takeoff, you have HP. Straightforward question. If aircraft cruising at maximum aerodynamic efficiency, all right, with peak power obtained in the last question, then what will be the speed? So looks pretty straightforward to me. Power is thrust multiplied velocity, and thrust can be written for the cruise like this. So only V is unknown for us because W is known. Because two of you already know where the expression came from. Sanjay, are you aware of this expression? How did it come? For thrust, this value. Because Om and Ripinder have been doing these sessions for quite a long time, so they're aware. Yeah, you are also aware. All right, so we are done with the assignment. It was pretty straightforward. How many you guys got correct? Ripinder?
Sir, I just didn't get the last one, but I get all rest of them correct.
Now you got the last one, right?
Yes, sir. This is the formula which I wasn't getting.
Okay.
But now
See, it's pretty straightforward thing, but
Yes,
we
sir.
actually keep forgetting these things in the exam.
Sir, I know about thrust, but I was confused for the power part.
Okay, okay.
But now I got it.
And how about Om? How many you got correct? He doesn't want to tell because maybe he got all correct. So he wants to keep it a secret. I don't know. Okay, so I think we can go back to the design problem we were solving. And yeah, so for Sanjay, it will be a little hard to catch up what we have done because he has to go through two sessions, the last two sessions. I'll upload that video of last session. I did not upload it so far, but it'll still give you some idea what we are dealing with here. So for everyone's clarity, I'll just repeat what we have done so far. Okay. So we want to complete the chapter 8 basically. Someone has done a very good job for writing this chapter for us, John D. Anderson. The chapter is design of a propeller driven airplane. Okay. And for this particular aircraft, we are given certain requirements: level speed, range, ceiling, rate of climb, stalling speed, landing and takeoff distance. So we are supposed to give a conceptual design for this aircraft. And by conceptual design, we mean what are the performance numbers, weight, CL by CD, wing loading, thrust loading, power requirements, right? Configuration of engines, number of engines, all of these questions. We answer these questions in the design. This process is called design. So In the very first session, we covered the weight estimation of the aircraft, and for you can see this expression again. E is the empty weight, F is the fuel fraction. So this fraction, the fuel fraction, is computed from the mission profile. Empty weight fraction is taken from historical data, and crew and payload weights are given to us because this aircraft was supposed to carry some people. They might have specified 5 passenger plus the pilot. So you know the crew and payload weight, right? So we did the weight estimation. And earlier also in the assignment question, I wanted to emphasize this philosophy, how aircraft weight is computed. You know certain weight fractions, and you have some known weights. So a combination of them can be utilized to get an idea of the total weight. Also, notice that the takeoff weight or the total weight of the aircraft is basically a factor of crew plus payload weight. So imagine W crew plus W payload, they are getting multiplied by a certain number. Let's say the total weight is 500 kg for the numerator. Then the total aircraft will be an amplification of that number, 500 kg. So if you increase the crew and payload weight, let's say by 10 kg, so your total aircraft weight will increase quite a lot, right, in terms of actual kgs. So I emphasized this during that session also. In aeronautical community, we want to keep the crew and payload weight as minimum as possible, right? The payload weight specifically. All right, and if we can minimize the empty fraction, we want to minimize that. And that is also true with respect to fuel. We want to optimize the design such that fuel fraction turns out to be very low. And same goes for structural optimization. So there is aerodynamic optimization involved here for fuel optimization, right? You want to have minimum CD naught, and same goes for structural. You want to keep the weight minimum, so you choose materials, shape and sizes of the objects that are required for the aircraft design very optimal, right? So you require less and less weight. So that's how you minimize the overall aircraft weight. So yeah, this was covered in the first session, and in the second session, we covered estimation of critical performance parameters, where we discussed about how to get a lift coefficient for maximum lift coefficient for a particular wing, and we have to choose an airfoil at this junction. So we went with 2 5-digit airfoils, a combination of these two different airfoils at root and chord, root and tip, and somehow averaging the CL for these two, because all other airfoils in between these two extreme sections, we could just take an average because flap was deflected, so the maximum CL will increase. We have data for those airfoils. We could safely compute the total CL. Now 3 defects are involved, and we are only computing the CL for 2D airfoils. So we take safely 90% of that total CL, right? So we were able to compute the CL max. Then we went for the wing loading, and during that we understood that what determines the wing loading. So we understood landing distance and Vstall. These two quantities dictate how much wing loading you should have. So we computed using both of these, landing distance and Vstall, and 2 numbers turned out. The 2 numbers are I think 29.3 and 41.5. So a lower wing loading is safe for us, right? So we went with that. Then we went for thrust to weight ratio, and thrust to weight ratio is dictated by takeoff, rate of climb, and maximum velocity. We did calculations for thrust to weight ratio using takeoff distance. We are given a takeoff distance, and we looked at the takeoff profile, and we were able to compute a almost 11% of almost 12% of thrust to weight ratio. Now we want to see whether rate of climb and maximum velocity constraints are also satisfied, because takeoff distance is giving us one thrust to weight ratio, rate of climb will give us another thrust to weight ratio, and maximum velocity will give us another thrust to weight ratio. Also, for rate of climb and maximum velocity, we need power, how much power our aircraft is going to required power. And based on the required power and efficiency, we will need the brake horsepower of the engine, right? So how powerful the engine we should have, it should be dictated by the takeoff distance, rate of climb, or maximum velocity. So whichever of these three phases require the maximum power, we will keep that power, because all other constraints can be satisfied with that. All right. So we had computed everything until here. So far we know the thrust to weight ratio, that is computed from takeoff distance, this T over W. We know W naught, or the takeoff weight of the aircraft, and we also know the because we have computed takeoff distance, so we know at what speed we want to fly, right? So it gives us the required power, and this required power, yeah. So how are we going to compute the available power from required power?
Yes, we multiply it with the propulsive efficiency.
Right. So we did that, and we are able to compute what should be the brake power, shaft brake power. And let's see how much is this number. We're able to see it's around 118 HP. So now we want to see how much power is required for rate of climb, because 118 HP engine would suffice for takeoff, given the weight and the velocity at which we want to take off, right? Now the question is, how do we compute the power from rate of climb? What is required? Any guesses? Wild guesses?
Sir, I know the formula for this rate of climb, which is rate of climb equal to v infinity into sine theta.
Okay.
Sine theta is the climb angle. So if we know the climb angle, we can divide it with the rate of climb, which will give us the v infinity. And power is also related to v infinity, as thrust into v infinity.
All right. So going ahead, we need zero lift drag coefficient for all those calculations. We'll see the actual expressions later on, but at this juncture, we need to estimate that. So in one of our sessions, I discussed about weighted aspect ratio. Anyone remembers that?
Yes, sir, weighted aspect ratio. Yes.
How do we define it?
Sir, it is the area which is in the airstream outside, which is interacting with the free airstream. We can say that.
Yeah. So, all right. For everybody's understanding, I'll just draw a picture. So, see, I don't know exactly. I'm not very good at drawings, but I still make the top view. So Okay, so the top view of a typical aircraft looks like this. Now, aspect ratio is usually defined like this, B square over wing reference area. And the wing reference area is this area, right? The area of the wings, right? Area of the wing. Yeah. Anything like area on the fuselage, area on the tail, area on the cabin. This is not covered in aspect ratio. So we define the aspect ratio again for the total area that is exposed to the air. Okay, and it turns out for the aircraft that we are trying to design from historical data. Remember, there is a source for everything that we are quoting, and the book refers to those tables where the data is being taken from. Either it is taken from earlier books or some resources like .com. Okay, so they are resources provided by NASA, and this is wing reference. So for the aircraft we are designing, this number is close to 4. So it's given here in the book. Wetted area is approximately 4 times of the wing area. Okay. Now the skin friction coefficient. Before coming to that, uh, zero lift drag coefficient is governed by what? What are the components in CD naught? The drag polar looks like this, right? So CD naught is driven by what? We are interested in CD naught, okay, at this juncture, and the goal is to compute power required for rate of climb, that is given almost 1000 in what unit? 1000 feet per minute. So to compute that power, we need CD naught. So right now we are focusing our attention to how to compute CD naught. So the first number we found out is the weighted area, ratio of wing reference area and the weighted area from historical data, which turns out to be 4. Now my question is, what drives CD naught?
Sir, mainly the air interacting with the surface of the air, surface of the body.
I mean, I don't know how to interpret this answer actually.
So the boundary layer friction, we can say that the air is rubbing between the fuselage and free stream, so it
So
will produce
is
some
there
friction.
any name for this in literature?
Yes, the skin friction.
Yeah, skin friction. So you can just say skin friction. Okay, so skin friction is the main contributor in CD naught. What are other contributors, by the way, in CD naught?
Sir, maybe there can be pressure drag.
Which
Or, pardon, sir?
uh, like the question was, apart from skin friction, what are other contributors in CD naught?
Sir, maybe pressure drag there could be.
How do you define pressure drag?
Sir, it is due to the pressure irregularities. Like there is negative pressure above and positive below. Also, the air is flowing over the airfoil. There is adverse pressure gradient, which is also creating some drag.
In simple language, you can say, let's consider a cylinder. Okay, air is coming at the front, going like this. Skin friction comes because of this interaction between air, right, on this skin. But the pressure drag comes because the velocity of air stagnates, right? So if I just look at incompressible regime of the flow, then pressure at any point here, it is stagnated, right?
Yes,
And there
sir.
is certain pressure, let's say PA and PB. So PB is higher than PA because PA, it has some velocity component also, right? I'm just looking at incompressible regime. Now, this pressure is higher than the pressure here because what happens is there is a wake, and in wake of this cylinder or aircraft or anything, wake of anything has less pressure. So there will be some vortices moving here and there, right, in this region. So pressure is low in this region. Now, because this is a blunt body, you are experiencing a backward force, right? The force in the direction of the air. You're experiencing a force. So that force is also drag. It's not because of the lift or anything. It's just because the shape has some surface area that is blocking the flow of air. It's pressure drag. It's because at the front of the body, air stops. At the back of the body, there is low pressure, right? So it is the pressure drag. But it's not very it's not a major component. Skin friction is a major component to CD naught. But let's see how do we compute it. So this skin friction coefficient, it is being taken from a table directly. Okay, skin friction coefficient from a table that's given. Now, how do you read data from the table? You read based on the Reynolds number that's relevant for this particular aircraft. So we have some idea about the length of it. Okay, and based on that, because we also know at what velocity we are flying, all of these calculations are being done for a velocity for cruise, right? So based on that, this is the Reynolds number. 10 to the power 7 is the Reynolds number we come up with. Now, if you have a different design, then you will have a different length and different Reynolds number and a different skin friction coefficient. And based on this skin friction coefficient and the area ratio between the wetted and wing reference area, there is a relationship for CD naught. Okay. And the equation is discussed in chapter 2 of this book. So you can refer to it. I don't really recall how it is derived, but I'm just giving you some sense. So CD naught is computed. What you have to remember is CD naught is driven by weighted area ratio and skin friction coefficient. So this is the CD naught. Now we also need K, this K. How do we go ahead and compute K?
Sir, K value is 1 upon pi EAR.
Yeah, perfect. It's given here. So we use that. We do you recall when L by D is maximum? So this expression comes from there.
Yes, sir, got it, sir.
So this expression only depends on CD naught and K. K is a non, CD naught is non. L by D, we know pretty much we have taken 14. During the range calculation, we had assumed a certain L by D. Not assumed for a typical aircraft, it's more than 10. So we took for safety 14. So L by D is known for us. CD naught we just computed. We can come up with K now. So K is known to us now. And because K is known to us, we can have a rough guess about the aspect ratio, because the definition of K was here. You see 1 over pi E aspect ratio, and this is equal to K. And how to take this efficiency, and what is this efficiency factor here?
Oswald efficiency factor.
And what should be its value? What value?
Sir, its value is 1 for an elliptical wing, but we don't know currently the shape of our wing.
Yeah.
So maybe
A
we
reasonable estimate is 60% here. It's written in the line here. A reasonable estimate for this efficiency, old Oswald efficiency for a low wing general aviation airplane is 0.6. So he has referred to a book. Okay, every number that we're taking from somewhere. So when you do a thorough study of this chapter, you can understand what are the references required to design this thing. But we are just looking at the philosophy, how it is done, right? We can refer these numbers later on, and we can even refine these numbers. But for a first guess of the airplane design, we can refer to the previous books. So aspect ratio turns out to be 7. And now we have an expression for rate of climb from chapter 5, equation 122. Okay. Now we understand, we need to know the power, right? So power or power to weight ratio, either of them, because we know that is the unknown for us. R of C is given to us because that is the specification. L by D is known to us. Everything is known to us. Okay. So we simply do algebraic manipulation and find out the power, assuming 80% efficiency. And the power turns out to be 362 HP. Do you remember what was the HP for takeoff?
118.8.
You see, now it is 362. So keep in mind, rate of climb requires more power than takeoff. Okay, because takeoff is very smooth. The rate of climb during takeoff is small, and you might require a larger rate of climb, right? So for that number rate of climb dictates the power. Now we want to make sure that maximum velocity constraint does not require. Yeah.
So this rate of climb is given at which altitude? Because density will vary and the power at the end will the thrust we will be getting reduced as the altitude will be increasing.
Yes, that is perfectly true. So since we are not looking at the altitude, so we go back and see the requirements list. What does it have to say? Rate of climb at sea level. Okay, so we are doing at sea level. The density is at sea level.
So can you just show the CL part here up above? Just I need to see.
CL of the aircraft.
Yes, sir.
Okay. Yeah.
Sir, they are taking average.
Yeah.
Okay, so they have chosen aerofoil already.
Yeah. See,
Okay.
the argument is in United States, these general aviation aircraft were using these 5-digit airfoils with almost 12 to 18% of thickness. Okay, so author thought to go with those airfoils only. So we are not going with one airfoil, but we have two different airfoils at root
For
and
root and tip, yes, sir.
yeah.
I remember it.
Mm.
And then we said that is for airfoil, then we convert it for the wing
Yeah.
by the formula.
Not by the formula, but by simply saying that uh, we are taking 90% of what was valid for a airfoil. Okay, so that's a rough guess actually.
Okay, sir.
Yeah, because see the complexity of the flow is much larger. Like it's not just a 3D wing and a 2D airfoil. That can be done actually with some expressions that are known to us, but it was found that 90% of that airfoil CL, it usually good. It is usually good. So now we were computing power. We have power from takeoff. We have power from rate of climb. Now we want to see whether maximum velocity violates the like how much power it requires. That's what we need to know. And maximum velocity, then question is again at what altitude. So altitude is specified here 20,000 feet. So what happens in cruise is thrust is drag, right? Thrust equals drag. We just put this expression using drag polar, and we substitute the CL in terms of weight, and we have this thrust to weight ratio. What we do is it also says that this maximum velocity is at mid cruise weight, not at the takeoff weight. So what we are doing is we max since the requirements stipulate we max at mid cruise weight. The value of W that appears in equation 8.48, this expression, uh, is less than the gross takeoff weight. So first we want to compute that mid cruise weight. And how do we do that? The procedure is already given in that weight estimation section. So we take the weight fractions for individual sections, takeoff, climb, and so on. So we do that procedure and we find out mid cruise weight WMC, and we compute thrust to weight ratio for using WMC. And other things are known to us as CD naught. Altitude is, sorry, the density is also known to us because altitude is known to us. And based on thrust, we compute the required power, right? TV naught is the required power. And from here, we want to compute that brake power using efficiency. And it turns out to be 303 HP. So maximum power is being consumed in rate of climb. So whatever engine satisfies rate of climb constraint, we will choose that. So this is the power we will, not this 362 is the power we will take for the engines of this aircraft that we're designing. So mainly don't basically get lost in the calculations here. You can always refer the book. The philosophy is, the constraint on power is from three different things. And as a designer, you have to look at all requirements and satisfy or convince yourself that, okay, now this is the power that I'm going with because it is maximum. All right. So here is the list to summarize the results from this section. The three constraints on power required for the airplane design for takeoff, rate of climb, and maximum velocity. You can also keep in mind this will be true for almost all general aviation aircraft. So you should have a relativity aspect in your mind, like in what maneuvers we require maximum power. Yeah. So he just converts it to power to weight ratio or power loading. So because everything is known to us as the total weight is also known to us, we end up this section summary of the critical performance parameters. So we begin with nothing. Yeah.
So at the end, which power we are taking? I think we should take the highest one.
Yeah, highest one, because if highest one is satisfied, then others are always satisfied. Like,
yes.
Yeah. So we are computing the available power, okay, based on the required power, because available power has to be higher than the when you have nothing, what you should refer, right? So we will end this session today here only. In the next session, we'll talk about configuration layout and other things from this chapter. You can give it a read, whatever we have covered so far, and you can read ahead also. So you can ask some good questions. We can have discussion on them. And thank you for joining. I'll stop sharing. You can leave the meeting now.
Thank you, sir.
Yeah, thank you for joining.
Sir, do we have any previous year questions available?
I'll try to give you maybe in the next session, or you can drop your email here so I can email you if I get access to it. Okay, I'll ask people. Yeah, because the TAs who work with professor are different people, and we do not know who makes the like, I know actually who makes the assignments, but we are not the ones who make them. So we just try to help you with the assignments. That's all.
Okay.
Yeah. You can drop your email. If I get access to it, I'll send you.
Yeah, sure.